Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the lecture 2 of module 4. In today's lecture, we are going to cover following concepts. We will be covering torsional modes. Spherical modes, normal mode synthetic seismogram, and we will also see some of the animations associated with normal modes, including torsional modes and the spheroidal modes. As far as the recap of the previous lecture is concerned, in the previous lecture we gave you an analogy of the ringing bell in the temple, and we saw that when the bell rings at specific frequencies, then it can produce some kind of sound waves which can still be used to infer what kind of material it is made up of. Similar to the bell in the temple, earth also rings like a bell after a great earthquake. Then we convert all the seismogram associated with that great earthquake to see what kind of frequencies are coming at what peaks, and all those peaks we indicate it by different kind of modes, either spheroidal modes or the torsional modes. After we do some kind of modeling of those peaks, we can usually infer about what kind of material is there in the earth, like what kind of density and what is the velocity variations within the earth and what kind of material the core is made up of. So we also gave you an information that the idea of the liquid outer core was probably first given by the study of the normal modes. So what are normal modes? Normal modes are the oscillation of the system and is some of the standing waves. So for example, whole earth vibration after a large earthquake, and also normal modes can be produced by free oscillation of the sun that we study in the field of helioseismology. So for displacement in 3D, we can define the displacement of the normal modes using a spherical coordinate system in r, theta and phi, where r is the radial direction, or you can say up and down direction in the surface of the earth. Theta is the co-latitude, phi is the longitude. So the summation on the n, l and m can be written by this particular expression in the form of displacement, and NLM defines the radial, angular and the azimuthal order. Similarly, this y expression here is the scalar radial eigenfunction, and XLM is the vector surface eigenfunction. And all these things are weighted by this amplitude, which is the excitation amplitude, and that can be found out using the position of the source, excitation of the source. So basically it depends upon the fault geometry where the earthquake is occurring. Now then we defined two types of normal modes. One is spheroidal mode, which is analogous to the P and SV motion. Then we defined toroidal modes, which is analogous to the love wave motion or predominantly SH wave motion. Then we used the boundary conditions on the string, which basically produce the various kind of modes, and those modes can sum up to form the traveling wave or the propagating waves. So the summation goes like this. Here you can see there is the spatial eigenfunction, and omega in the spatial eigenfrequency, cos omega nt defines the sinusoidal wave, and the spatial eigenfunction is defined by sine omega nx by v, and omega n is n pi v by l, which means that the eigenfrequencies are separated by pi v by l values. Similarly, in the case of spherical harmonics, for defining the normal modes, the spherical coordinate system we can choose is the orthogonal coordinate system, in which we can define the spherical harmonics using this expression, which is this particular term is the Legendre polynomial we saw in the previous class, and e to the power iota m phi defines the attenuation factor that may be associated with the waves hello hello yes sir. Okay sir. Okay sir, actually I am in the recording room, so maybe I will be 5 or 10 minutes late, but I will be there. Okay sir, okay sir, okay, okay sir. So similarly, fully normalized and orthogonal spherical harmonics for Earth can be given by this expression here. Mhm. Similarly, fully normalized and orthogonal spherical harmonics for Earth is given by this particular expression. Here, this particular expression defines the legendary polynomial, which is having another product, that is e to the power iota m phi, and this entire expression represents the spherical harmonics, where n, l and m are the radial, angular and the azimuthal order. Now let's move on to the topics of today's lecture, where we are first going to discuss about mode separation. As you can remember, in our previous module, we talked about the surface waves, where we saw there are two kinds of surface wave. One is Rayleigh wave, another wave is the Love wave. Rayleigh wave basically consists of the two kinds of motion, P wave motion and the SV wave motion. Similarly, the Love wave consists of SH wave motion, and these motions can be separated out for Rayleigh and the Love wave, and we can perform the same thing with the normal modes as well. So in the case of normal modes, there are two kind of modes possible. One is the spheroidal mode, another one is the toroidal mode. So the expression for the spheroidal mode can be indicated by this, and for toroidal mode it can be indicated by this. So spherical mode has horizontal, which also known as tangential motion, and also consists of the vertical or the radial component to the motion. In contrast to the spheroidal mode, toroidal mode have no radial component to the motion and is confined to the surface, having the n concentric spheres within the Earth. The spheroidal mode doesn't have any simple relationship between n and the nodal spheres, while the toroidal mode do not have any volume change. So which means that the spheroidal mode, so because it consists of P and SV wave motion, it has the volume change. The fundamental mode associated with the spheroidal mode is 0s2, where m is equal to 0, and it affects the whole Earth from the surface to the core, which means it does include the volume change. On the other hand, the toroidal mode do not exist in the fluid, because we know the shear wave do not exist in the fluid because of the absence of the shear. So they do not exist in the fluid, since fluid cannot have shear. What are the physical effect of N, L and M? In the case of spheroidal mode, N do not have any direct relationship with nodes with depth. L, which indicates the number of nodal planes in the latitude, which are also known as singlet, while M, number of nodal planes in longitude, which varies between -L to +L. That means total number of M values are 2L plus 1, and they together are known as multiplet. While for the toroidal mode, the N indicates the nodal planes with depth. L, the number of possible values are L minus 1 in the toroidal mode case. So that it indicates number of nodal planes in latitude, which is indicated as singlet, while M are the number of planes in longitude, which varies between -L to +L, and also known as multiplet. So this is, you can see, these are the fundamental mode for spheroidal and also for toroidal mode. And this particular mode, also known as the football mode we have seen in the previous lecture. And this particular mode is like the material in the middle is moving in the opposite direction to the material near to both of the poles. So let's talk about the torsional or the toroidal mode, which is analogous to the SH wave. The surface eigenfunctions given by a vector spherical harmonic. The toroidal mode can be represented by this particular expression, where the first term is 0. That is basically seems true because it doesn't involve any P or SV wave motion. So the first term associated with the radial component should be 0. The other terms would be having some finite values. The displacement associated with the toroidal mode can be given by ut as a function of r, theta and phi, which will be a summation over n, l and m, where m will be varying from minus l to plus l. That will be having the amplitude term, radial eigenfunction term, and also will be consisting of phi and theta motion, and which includes this toroidal mode as well. So where u that we are seeing over here can be separated out in the form of ur, u theta and u phi, and the term radial eigenfunction is very complex and it will be having very complex calculations, so we will keep it out from our discussions for now. So as far as the torsional mode is concerned, as we have seen, n is the radial order, l is the angular order, m is the azimuthal order. So total number of variations for m will be from minus l to plus l, and the total number of modes for the values of m will be possibles are 2l plus 1, and all these values will be now called as singlets, and the group of the singlets are basically multiplets. So in case of the solid non-rotating earth that is isotropic in nature, all singlet in a multiplet would have the same eigenfrequency. That means if you keep L and N values constant and will vary M from minus L to plus L, then all the modes associated with these values of N, L and M will be having the same eigenfrequencies if the earth is solid, spherical, non-rotating and also isotropic in nature. And this particular property is also known as degeneracy. And if suppose the earth is not spherical or not spherically symmetric, then there will be no degeneracy. So as I told you, if you are varying M from minus L to plus L for constant values of L and N, then all the modes will appear at the same eigenfrequency, and that will be called as the degeneracy in case of solid, spherically symmetric, non-rotating and isotropic earth. So, but what will happen in the case of the real earth situation where the earth is aspherical, which means not symmetric, not spherically symmetric, and also it is rotating in nature, and you know earth is anisotropic in nature, then what will happen in that case? All the values associated with the constant L and N, where M is varying from minus L to plus L, all the modes, all the singlets will be separated out, or you can say all the singlet of a multiplet will be separated out. So you can see in this figure, this is for 0s2 multiplet, and in this case 0s2 where M is varying from minus 2 to plus 2. So all the singlets are basically separated out. In the case the earth is asymmetric, anisotropic and rotating in nature. So that is because of this we can see all the frequencies are varying, and this particular phenomena is known as splitting. So for example, the period of n t0l would be same for n l plus 1 minus 1, for all n and n plus 2 minus 2, and for plus 3 and minus 3, all will be having the same period. But in case of real earth, the frequencies of all these modes will be different, will be varying, and this phenomena is known as splitting. So the splitting is usually small enough to ignore. So we can drop the m superscript and refer to entire NTLM multiplied as NTL only with eigenfrequency omega. Now let's see some examples of splitting. So one thing that I should mention about the solid non-rotating earth that is isotropic in nature, this can be abbreviated as SNREI, SNRE. And in this case, as I told you, for the constant value of L and N, where M is varying from minus L to plus L, all the modes will be appearing at the same eigenfrequency, and this phenomenon is known as degeneracy. So the phenomena of degeneracy happens only for the case of SNREI earth, which means the earth is solid, spherical, non-rotating and isotropic in nature. Now let's look at this particular figure here, which is basically the graphical representation, or you can say the pictorial representation of what we have learned just in the previous slide. So splitting happens because of the rotation phenomena of the earth. It happens because of the ellipticity of the earth, and also it happens because of 3D variations in the earth. Now look at this particular figure here, which is taken from Stein and Weissation. This is the amplitude spectra of 9 singlet of the split spheroidal modes multiplied 18 as 4, where M is 18 and L is 4. So where you can see the value of M is varying from minus 4 to plus 4. So this is your 18 as 4. So this L is 4. So M will be varying from minus 4 to plus 4 here. So you can see associated with each value of M, we have these pulses, these peaks here in this particular figure. So the peaks associated with minus 4 singlet is at the front. That means that this one at the front. And the peak associated with plus 4 is kept at the back of this particular figure. Now you can see, although the M values are varying and L and N values are kept at constant values, this should, in the case of SNREI spherical earth model, it should appear at the same frequency. But because earth is aspherical, inhomogeneous, anisotropic and also rotating in nature, so all these peaks are basically appearing at different frequencies on the x-axis, and this particular phenomena is known as splitting. Now look at this particular figure here, which is also taken from the Stein and Weissation book, and this is for the mode 0S2, which is calculated from the great 1960 Chilean earthquake. And this phenomena shows in the observed seismogram the case of splitting for 0S2. So you can see the mode has been split out here. This is one mode. This is for M is equal to plus 1. And in this case, you can see the splitting is causing these singlets, and those are stand out to be distinct peaks in the observed seismogram. So if you want to compute a synthetic seismogram by predicting the singlet amplitudes and combining them in the time domain with the effect of attenuation and finite seismogram length, then what you can see that this is your observed data here, which came out from the Chilean earthquake data, real earth data, and this is the synthetic data that we computed when we considered the case of splitting. Also we considered the case of attenuation. Then after you incorporate both of the phenomena of attenuation and the splitting, then you can better synthesize your seismogram that can match very well with the observed seismogram here. In case if you are not considering the phenomena of splitting, then your synthetic seismogram may look something like this, which is not matching with the observed seismogram. Now, these are some of the examples of the torsional modes. When n is equal to 0, then the torsional modes will be known as the fundamental mode. So this is your fundamental mode. This is also your fundamental mode. This also fundamental mode. These two are also fundamental mode. And modes with n is greater than 0 are called as overtones. So in case of overtones, the material at different depth will be having the different directions. So you can see this is the overtone. This is also another overtone of the torsional mode. Now let's talk about the spherical mode, which is also known as poloidal mode, which involves P and SV motion. So you can understand the displacement will be having the two terms. One is for the radial motion, another one is for the horizontal motion. So the radial motion can be represented by this particular expression, where you can see the motion associated with theta and phi are 0, or you can say the motion associated in latitude and longitude or the angular motions are 0. And for spherical and for the spheroidal one, you can see there is no radial term here. So only the non-zero terms are this one and this one. So this each corresponds to a different radial eigenfunction u and v. So the displacement for the spheroidal mode is having this expression, where you can see this is for the radial motion, this is for the horizontal motion. Now let's look at some of the example poloidal or the spherical mode. 0s2, which is also known as football mode. We have seen it couple of times in the previous slides. So this is basically the gravest mode of the earth, which has period of about 54 minutes, and it is also known as football mode, and it can be represented as something like this, and in the motion picture it can be something like this. So you can see the poles are expanding, at the same time the equatorial positions are contracting. When the equatorial positions are expanding, the poles are basically contracting. So there is no 0s1 mode, which would correspond to a lateral translation of the planet. 1s1, which is also known as the Schlichter mode, due to the up and down motion of the inner core through the liquid iron outer core, which has yet to be observed, should in principle has the period of about 5.5 hours. And 0s2 can be represented like this, and 0s2 with L is equal to 2, which basically has the representation like this, which is similar to the beach ball. Now let's see, this is the breathing mode here, which is represented by 0s0, which involves the radial motions of the entire earth that alternate between expansion and contraction. And 0s0 is this mode, which is, as I said, also known as the breathing mode, and it may look like something like that the entire earth is expanding at the same time, at the another time it is contracting, and it can be represented something like this. 1s0 is this mode, where the material near to the surface is expanding, but at the same time at depth the material is going in the reverse direction, that means contracting. So now how the normal modes are useful. Frequencies of the normal modes can tell us about the shape of the earth, also can talk about the bulk modulus, can also tell us about the shear modulus of the material in the earth, also can talk about the density variations in the earth. Normal mode can also help us with the following. It can simulate the phenomena like diffraction, which is not possible with the case of ray theory. Also, the eigenfrequencies in the normal modes are sensitive to the earth structure in a way that complement other methods. More efficient way of creating synthetic seismogram, although there are various methods of creating synthetic seismogram, but normal mode summation method is considered to be very efficient way of creating synthetic seismogram that correspond to a long time period or for long period surface waves. It can be used to infer distant earthquake focal mechanisms, and it also can be used to infer earthquake magnitudes. So to calculate the synthetic seismograms using normal modes, we can use the technique that is known as normal mode summation, which is analogous to the way the propagating waves on the string were generated. So spheroidal mode displacement can be synthesized using this expression, where this expression is the attenuation of the mode, and the expressions like W and omega are representing the radial eigenfunction and the mode's eigenfrequencies that can be determined by Earth's velocity and the density structure. As I told you, this expression is the attenuation of the mode, where there is a particular term Q. This term Q, this 2 should not be here. So this particular term Q is the quality factor of the mode that measures the rate at which the mode's energy is lost by friction. So the Q cycles of oscillation means the amplitude of a mode has fallen to a level of 4% of the original amplitude. So that means when the Q number of cycles or the oscillations will happen in the mode, that means the amplitude will decay to 4% of the original amplitude. These modes are weighted by the excitation magnitude, that is A. The value of A can be determined by the depth, geometry, and the time history of the seismic source and the depth of the receiver. This formulation assumes that all signets in a multiplet have the same quality factor. Now look at this particular diagram, which is also taken from Stein and Weiss session. It is the example of modeling data with the normal mode summation technique. So this is your radial component, this is the north-south component, and this is the east-west component. And in this particular diagram, or in the seismograms, you can see there are the two seismograms. The top one is associated with the observed data. This one is also for the observed north-south component, and this is for observed east-west component, while the bottom one, this is for the synthetic vertical component, synthetic north-south component, and this is for synthetic east-west component. And you can see, using the normal mode summation technique, the fits are very good, and that is enough for the studies that uses observed normal mode amplitude to find the fault geometry and fault depth, focal depth of the earthquakes, and especially when they are large and remote from the seismometers. And in general, what we do, we keep our receiver to compute the synthetic seismogram at the surface, but you can also keep your receiver at various depth. So this particular diagram is representing the receiver kept at starting from the surface to the core mantle boundary depths. So these are basically showing us the example of synthetic seismograms computed using the normal mode summation technique for an earthquake that is around 70 degrees away from the receiver. And this is just the pictorial form of the seismograms using normal mode summation technique. These are some of the animations for just to give you an idea how the normal modes look like. So you can see this is the fundamental mode of spheroidal mode, which is having the 20 minutes of period, which is expanding and contracting at the same time at the different times, starting from the core to the surface. Now this is another animation for the spheroidal, this one. Here the value of n is 1, the period is 10 minutes. And this animation is for the torsional mode, where n is equal to 1, L is equal to 1, and the period is 8 minutes. So these are the references. And we will learn about the normal modes and how do we calculate various kind of spheroidal mode and the torsional mode and also associated displacement in the next class. We will do some calculations in the next class or the next lecture. Thank you so much. Bye bye.